In January 2025, astronomers detected something moving through our solar system. Came from outside, not from the Kuiper belt, not from the Oort cloud, not from anywhere within the gravitational embrace of our sun. This object originated from interstellar space, a traveler from the void between stars, the third confirmed visitor in human history. They named it 3I/Atlas. Within weeks, observatories around the world turned their instruments toward this cosmic wanderer. Data began flowing. Trajectory calculations were refined. And for a brief moment, everything appeared routine. Another interstellar object. Another scientific curiosity. Another entry in the catalog of things that pass through our cosmic neighborhood. But then something changed. Buried within tracking logs from a European observation network, researchers discovered a notation that was never meant to be seen. A designation that appeared in internal documents but was absent from every public report. A simple label that raises a question no one has officially answered. Object B. If 3I/Atlas is a single interstellar object, why would tracking notes reference a second one? That question led to others. Brightness curves that behave strangely. Trajectory refinements that required unusual corrections. Gravitational calculations that suggest the presence of something we cannot see. And a faint secondary signature that appears in certain imaging passes, then vanishes. There are 6 documented anomalies surrounding 3I/Atlas. 6 pieces of data that do not fit the standard model. 6 cracks in the official narrative that most astronomers have chosen not to discuss publicly. By the end of this video, you will understand each of them. You will see what the tracking data actually shows. You will examine the 3 hypotheses that attempt to explain these irregularities. The vast emptiness that contains more volume than all the galaxies combined. It will drift for millions more years, perhaps billions, until some other gravitational encounter deflects it again, toward some other star, some other system, some other civilization that might look up and wonder what it was. We are fortunate to have seen it at all. 3 interstellar objects in human history, 3 visitors from the void, 3 chances to glimpse what lies beyond our tiny neighborhood. That is not many, but it is enough to know they exist. Enough to know the space between stars is not empty. Enough to know that objects cross the darkness, that they have always crossed, that they will continue crossing long after we are gone. Perhaps 3I/Atlas carries secrets we will never unlock. Perhaps the companion object, if it exists, represents something beyond our current understanding. Perhaps the anomalies point toward discoveries that will reshape our view of the cosmos. Or perhaps not. Perhaps it is simply a rock. A strange rock with unusual properties. But ultimately just another piece of the universe doing what pieces of the universe do. Falling through space. Obeying gravity. Following the laws that govern everything. We may never know with certainty. But we will watch. We will gather data. We will refine our models and test our hypotheses and argue about interpretations. Because that is what we do. That is how we learn. That is how we push back the darkness one observation at a time. And somewhere out there, 3I/Atlas continues its journey, carrying its secrets, keeping its silence, a messenger from the stars that may or may not be traveling alone. The universe does not owe us answers. But sometimes, if we watch carefully enough, it offers glimpses. This has been one of them. Rest now. The stars will still be there tomorrow. We gain extended observation time as the system moves outward. Further study becomes possible. If the companion exists and separates, we might witness fragmentation in real time. Dramatic confirmation of the binary hypothesis. A scientific spectacle. If nothing unusual occurs, the skeptical model may be correct. 3I/Atlas may simply be a strange solitary rock, and the anomalies may reflect our observational limitations rather than hidden companions. And then comes 2027, the perihelion approach. If there truly is a companion object, that's when the gravitational stress will reveal it. Take a slow breath. Let the questions settle. We have traveled far tonight, from the first detection of a wandering point of light, through 6 anomalies that challenge our expectations, through skeptical explanations and unsettling hypotheses, through checkpoints that will determine what is real and what is illusion. And now we rest. 3I/Atlas continues its journey. Regardless of what we believe, regardless of what we hope, it moves through the darkness on a path determined billions of years ago, a trajectory shaped by forces we can calculate but cannot touch. If there is a companion, it travels alongside, silent, unseen, bound by gravity across distances we struggle to comprehend. 2 travelers from a distant origin, passing through our neighborhood like shadows crossing a lit window. If there is no companion, 3I/Atlas journeys alone, as it always has, a solitary fragment of some ancient system, ejected long ago by forces we can only imagine, wandering the void until chance brought it within range of our instruments. Either way, it does not stay. Perihelion comes and goes. The sun's gravity bends the path but cannot capture it. 3I/Atlas will accelerate away, past the orbit of Mars, past Jupiter, past Saturn and Neptune and the frozen edge of our solar system. And then it will be gone, returned to the interstellar medium, the space between stars. If the secondary signature from the April 2025 imaging was real, JWST should confirm it. If it was instrumental noise, JWST should see nothing. This is the first critical checkpoint. If JWST detects a companion, hypothesis A or B becomes strongly favored. The binary or debris field model gains substantial support. The mystery begins to resolve toward a natural explanation. If JWST detects nothing, either the companion does not exist, or it is too small and dark for even Webb to observe. The skeptical model gains strength. But the other anomalies remain unexplained. October 2026. The thermal clarity window. As 3I/Atlas moves outward from its closest solar approach, thermal interference from the sun decreases. Background radiation drops. Faint signals become easier to isolate. This period offers optimal conditions for spectral analysis. If the companion object is outgassing, October 2026 provides the best opportunity to detect those emissions. Even faint molecular signatures might become visible against the quieter thermal background. If outgassing is detected, the non-gravitational acceleration is explained. The companion is a natural body releasing volatiles. Mystery solved through conventional chemistry. If no outgassing is detected, the acceleration source remains unknown. Hypothesis C retains its uncomfortable plausibility. Late 2027. Perihelion approach. This is the ultimate test. As 3I/Atlas reaches its closest point to the sun, gravitational stress intensifies. Solar radiation peaks. Any loosely bound material will experience maximum strain. If 3I/Atlas is a binary system, the gravitational interactions between primary and companion will become most pronounced during perihelion. Orbital dynamics will shift. Relative positions will change. The secondary body, if it exists, will be most influenced by solar gravity. This creates opportunity for detection, and it creates risk of separation. If the companion exists and survives perihelion, this hypothesis does not specify what that something else might be. It does not leap to conclusions about artificial origin or deliberate design. It simply acknowledges that we cannot determine the companion's nature from current data, and it holds space for possibilities that lie outside our standard categories. Perhaps the companion has an unusual composition we have not encountered before. Perhaps its formation mechanism differs from anything in our models. Perhaps its relationship to 3I/Atlas is more complex than simple gravitational binding. Hypothesis C is not a claim. It is an acknowledgement of ignorance, a recognition that the data permits interpretations we are not comfortable considering. Most astronomers reject hypothesis C as unnecessary speculation. The data does not require exotic explanations. Occam's razor favors the simpler interpretations. But hypothesis C remains logically possible. And until we have better data, it cannot be eliminated. But if hypothesis C is correct, then we've been asking the wrong question. By October 2026, 3I/Atlas will have moved far enough from the Sun for thermal interference to drop. That's when hypothesis C faces its final test. The story of 3I/Atlas is not finished. We stand at an intermediate moment. After initial detection, after preliminary analysis, but before the observations that will determine which hypothesis survives. The coming months and years will bring answers, or they will deepen the mystery. Either way, specific events will shape our understanding. Here is what to watch for. March 2026. The James Webb Space Telescope Observation Window. JWST possesses the most sensitive infrared instruments ever deployed in space. If a companion object exists near 3I/Atlas, Webb has the best chance of detecting it directly. The scheduled observation window will capture deep imaging in multiple wavelengths, thermal signatures, spectral analysis, high-resolution photometry, traveling together through interstellar space. Binary asteroids are common in our own solar system. Approximately 15% of near-Earth asteroids have companions. They form through collisions, through gravitational capture, through rotational fission when a spinning body breaks apart. If 3I/Atlas originated in a distant stellar system, it could easily have formed as a binary. Two fragments of the same parent body, bound together since birth, traveling as a pair for millions or billions of years. This hypothesis explains all 6 anomalies. The irregular brightness comes from 2 overlapping light curves. The trajectory shifts reflect binary orbital dynamics. The gravitational mismatch indicates the companion's mass. The acceleration comes from outgassing on the secondary body. The detection signature is the companion itself. Elegant, simple, requiring no exotic physics. If hypothesis A is correct, 3I/Atlas is unusual only in being our first detected interstellar binary. Strange but not mysterious. Rare but not inexplicable. Hypothesis B. Stranger. 3I/Atlas is not a binary but a debris field. A larger parent body that fragmented during its interstellar journey. Multiple pieces traveling together in loose formation. This would explain why the secondary signature appeared in only 3 frames. The debris might be spread across thousands of kilometers. Individual pieces might tumble in and out of detectability depending on their orientation. It would also raise questions. What caused the fragmentation? How long ago did it occur? What does the debris distribution tell us about the original body? Hypothesis B is less elegant than hypothesis A, but it remains within the boundaries of known physics, natural processes, understandable mechanisms. Hypothesis C, the most unsettling. The companion object is not natural debris, not a fragment of the primary, not a gravitationally captured rock. It is something else. In a field that generates millions of data points, 2% anomalies appear constantly. This is the skeptical position, and it is reasonable. It does not require exotic explanations. It does not invoke companion objects or hidden masses or interstellar mysteries. It simply asks us to accept that observational astronomy is difficult, that interstellar objects behave strangely, that our instruments have limits. Many astronomers find this position satisfying, prudent, scientifically conservative. But it has a problem. It does not explain why all 6 anomalies point in the same direction. Random measurement errors should scatter randomly. Instrumental artifacts should produce inconsistent results. Noise should behave like noise. The anomalies surrounding 3i/Atlas do not scatter. They do not behave inconsistently. They converge. They align. They tell a coherent story that the skeptical model cannot easily dismiss. The brightness curve suggests multiple light sources. The trajectory refinements suggest additional mass. The gravitational mismatch confirms additional mass. The non-gravitational acceleration suggests external pushing. The object B notation suggests someone took the possibility seriously. And the secondary signature suggests something was actually detected. 6 independent lines of evidence, all pointing toward the same conclusion. The skeptical explanation works until you reach anomaly number 5, because coincidence has limits, and 6 aligned coincidences begin to look like something else. Now we climb the ladder of possibility. What follows are hypotheses, not facts, not confirmed observations, interpretations of ambiguous data that attempt to explain what we have seen. Each will be clearly labeled. Each will be presented with appropriate uncertainty. But some possibilities are more unsettling than others. Hypothesis A, the most normal explanation. 3i/Atlas is a natural binary object. 2 rocks gravitationally bound to each other. The conventional interpretations. The reasons why most professional astronomers have not publicly embraced the companion object hypothesis. The skeptical case is strong. We should not pretend otherwise. Consider the brightness curve irregularities. Strange as they appear, they are not unprecedented. Oumuamua displayed similar behavior. Tumbling asteroids with highly irregular shapes can produce unexpected brightness patterns. An elongated object with varying surface albedo could explain the variations without invoking a second body. Consider the trajectory refinements. Interstellar objects are inherently difficult to track. They move at extreme velocities. They appear at vast distances. Small measurement errors compound over time. The systematic deviations we observed could simply reflect the limits of our observational precision rather than evidence of an unseen companion. Consider the non-gravitational acceleration. While 3i/Atlas shows no obvious outgassing, absence of evidence is not evidence of absence. The object could be releasing volatiles in forms we cannot easily detect. Carbon monoxide, molecular nitrogen, exotic ices that vaporize without producing visible signatures. The acceleration might be entirely self-generated. Consider even the leaked object B notation. Internal tracking systems often create placeholder designations for hypothetical scenarios. The notation might represent nothing more than procedural caution, a contingency entry that was never intended to indicate actual detection. And the secondary signature in the imaging data. 3 frames out of 17. Right at the detection threshold. This is exactly the kind of marginal result that instrumental artifacts produce. Cosmic ray hits, detector noise, optical ghosts from bright nearby stars. The probability analysis suggested less than 2% chance of random occurrence. But 2% is not 0. But they did share their results internally, and the designation in the leaked tracking log suddenly made sense. Object B was not a placeholder. It was not a precautionary notation. It was a reference to something that had actually been detected. Faintly, briefly, in 3 frames out of 17. A companion object, traveling alongside 3i/Atlas through interstellar space. Now watch what happens when we connect these 6 anomalies. The brightness curve is irregular because we are receiving light from 2 sources, not 1. The trajectory refinements keep shifting because the gravitational models assume a single body. The object B notation exists because someone detected evidence of a second object. The gravitational mismatch occurs because an unseen mass is tugging on the primary. The non-gravitational acceleration happens because the companion is outgassing, pushing the system. And the secondary signature appears because, for 3 brief moments, our instruments were sensitive enough to capture what is normally invisible. 6 anomalies. 1 explanation. 3I/Atlas may not be alone. In March 2026, the James Webb Space Telescope is scheduled for a dedicated observation window. If the secondary signature is real, that's when we'll know. But here is what troubles researchers most. If there is a companion object, where did it come from? Did it form alongside 3I/Atlas in some distant stellar system? Did it break away from the primary during the long interstellar journey? Or is its origin something else entirely? And that's when one researcher noticed something no one was supposed to see. Let us be honest about uncertainty. The 6 anomalies we have examined are real. They exist in the data. They have been observed by multiple instruments across multiple observation windows. This is not disputed. What is disputed is their interpretation. And before we explore the more unsettling possibilities, we owe ourselves a thorough examination of the mundane explanations. The gravitational mismatch and the non-gravitational acceleration. All 3 anomalies unified by a single explanation. A companion object, Object B, but we had no direct evidence of its existence. No image, no spectrum, no confirmed detection, until anomaly number 6. Because the next anomaly doesn't just break the pattern. It suggests the pattern was never what we thought. Anomaly number 6. The secondary detection. In April 2025, a deep imaging campaign was conducted using one of the world's most sensitive optical telescopes. The goal was simple: capture the highest resolution images of 3I/Atlas possible. Study its surface. Determine its rotation. Measure its true size. The images were stunning. 3I/Atlas appeared as a faint but distinct point of light against the star field. Motion tracking confirmed its interstellar trajectory. Photometry refined the brightness estimates. But in 3 of the 17 imaging passes, something else appeared. A secondary signature. Fainter than 3I/Atlas by approximately 4 magnitudes. Positioned within 2,000 kilometers of the primary body. Visible in frames 12, 13, and 14. Absent from all others. The detection was tentative. Right at the threshold of instrument sensitivity. Could have been noise. Cosmic ray hit. A background star briefly aligned with the target coordinates. But statistical analysis suggested otherwise. The probability of random noise producing that specific signature in those specific frames was calculated at less than 2%. The probability of a background star alignment was even lower. Something was there. Something faint. Something close. Something that appeared and then vanished. The researchers who conducted the analysis did not publish their findings. The detection was too uncertain. The implications too significant. Publishing a claim about a second interstellar object based on marginal data would invite professional ridicule. The one that demands explanation and resists easy answers. When an object moves through space, its motion is governed by gravity. The sun pulls it inward. Planets tug it sideways. These forces are predictable, calculable. They determine the object's path with mathematical precision. But 3I/Atlas was accelerating in ways that gravity could not explain. The deviation was first noticed in late February 2025. As the object moved past the orbit of Mars, its velocity began to increase slightly faster than gravitational models predicted. Not dramatically, not in ways that suggested propulsion or deliberate control, but measurably, consistently, in a direction pointing roughly away from the sun. For a comet, this would be unremarkable. Solar heating vaporizes surface ices. The escaping gas creates a jet effect. The comet accelerates slightly as it pushes against its own exhaust. This is called non-gravitational acceleration, and it has been observed in countless cometary bodies. But 3I/Atlas showed no evidence of outgassing. No coma, no tail, no spectral signatures of vaporizing ice. The object appeared dry, inert, rocky. So what was pushing it? Several hypotheses emerged. Perhaps the outgassing was occurring in wavelengths that instruments were not detecting. Perhaps the jets were so faint that they fell below observation thresholds. Perhaps the surface composition included exotic ices that vaporized without leaving typical signatures. Each hypothesis was plausible. None was confirmed. And then a more troubling possibility was raised. What if the acceleration was not coming from 3I/Atlas itself? What if it was coming from something else? If a second object was traveling nearby, and if that object was outgassing, its jets could impart momentum to the system as a whole. The primary body would accelerate without showing any evidence of outgassing itself. The companion would do the pushing. The primary would receive the push. This would explain the trajectory deviations, measured in fractions of arc-seconds. But it was consistent, and it pointed in a specific direction, toward something that was not in the models. Standard explanations were applied. Measurement uncertainty, instrument calibration drift, atmospheric distortion during ground-based observations. Each of these factors was examined. Each was found insufficient to explain the full magnitude of the mismatch. What did explain it was simple, elegant, and deeply troubling. An additional mass. If a second object was traveling alongside 3I/Atlas, its gravitational influence would tug on the primary body. The closer the companion, the stronger the effect. The more massive the companion, the more pronounced the deviation. Working backward from the observed mismatch, researchers estimated the hypothetical companion's parameters. Mass somewhere between 5 and 15% of 3I/Atlas itself. Distance somewhere between a few hundred and a few thousand kilometers. Close enough to exert measurable influence. Far enough to remain undetected in standard imaging. This was not proof of a second object, but it was consistent with one. The trajectory mismatch behaved exactly as it would if 3I/Atlas was not alone. If something was traveling with it. If the designation object be referred to something real. And the next anomaly would make that possibility even harder to dismiss. Keep that notation in mind. It matters later. Take a slow breath. Let the pieces settle. We have covered 4 anomalies. The strange brightness curve. The systematic trajectory refinements. The leaked object B notation. And the gravitational mismatch that suggests an unseen companion. Now we enter the data stack. The technical observations that transformed speculation into serious scientific consideration. Anomaly number 5. Non-gravitational acceleration. This is perhaps the most significant irregularity in the entire dataset. The one that echoes most strongly with the mystery of Oumuamua. The leaked notation. In March 2025, a document surfaced from a European observation network. It was not meant for public distribution. An internal tracking log. A routine administrative file that somehow escaped the boundaries of institutional confidentiality. Most of the document was unremarkable. Observation timestamps, coordinate refinements, telescope allocation schedules, the mundane paperwork of professional astronomy. But buried on page 17 was a single line that changed everything. Object designation, 3I/Atlas A. Secondary tracking, 3I/Atlas B. Status, unconfirmed, 3I/Atlas B. A secondary designation, a separate tracking entry, an acknowledgement that someone, somewhere, was monitoring the possibility of a second object. The document provided no further details, no coordinates for object B, no brightness estimates, no spectral analysis, just a designation, placeholder, a ghost in the tracking logs that was never officially announced. When questioned, the observation network declined to comment. The document was removed from circulation, and the astronomical community largely moved on. But the designation remained, archived, screenshotted, preserved by researchers who understood its significance. If there was no second object, why create a tracking designation for one? If Object B was merely a precautionary placeholder, why was its status listed as unconfirmed rather than non-existent? And why was the document handled with such obvious sensitivity? These questions lead directly to anomaly number 4, the gravitational mismatch. When astronomers calculate the trajectory of a moving object, they account for all known gravitational influences: the Sun, the planets, major moons, even large asteroids if they pass close enough. Every mass that might tug on the object is included in the model. For 3I/Atlas, these calculations produced a persistent error. The object was not moving exactly where it should have been. The deviation was small, but that brightness curve was about to reveal something else entirely. There are 6 documented anomalies surrounding 3I/Atlas. 6 observations that deviate from expected behavior. 6 data points that have quietly troubled researchers since the earliest weeks of tracking. 6 cracks in the foundation of what should be a straightforward interstellar encounter. We are going to walk through each of them, one by one, in order of discovery. And by the time we reach the 6th anomaly, you will understand why a small group of astronomers began questioning everything they thought they knew about this object. This is anomaly number 1, the brightness curve. Every astronomical object has a brightness signature. As it rotates, different surfaces catch sunlight at different angles. This creates a predictable pattern, a rhythm, a mathematical fingerprint that tells us about the object's shape, rotation period, and surface composition. For most asteroids, this curve is smooth, predictable. It rises and falls with clockwork regularity as the object tumbles through space. The brightness curve of 3I/Atlas is not smooth. Initial observations showed variations that did not match any simple rotation model. The brightness would increase when calculations predicted it should decrease. It would hold steady during periods when it should have fluctuated. And on several occasions, it spiked sharply for reasons that no surface geometry could explain. Astronomers attempted to fit the data to various rotation scenarios: tumbling motion, a highly elongated shape, an irregular surface with extreme albedo variations. None of these models produced satisfactory results. The curve behaved as though something was interfering with it, as though the light we were receiving was not coming from a single predictable source. This was unusual, but it was not unprecedented. Oumuamua had also displayed strange brightness variations. Perhaps interstellar objects simply behaved differently than their solar system counterparts. That explanation held for several weeks, until anomaly number 2 appeared: the trajectory refinements. As mentioned earlier, each new observation window allowed astronomers to refine their orbital calculations. This is standard procedure. Early estimates are always imprecise. More data produces better models. But the refinements for 3I/Atlas followed an unusual pattern. Normally, trajectory estimates converge over time. Early measurements are scattered. Later measurements cluster tightly around the true path. The uncertainty shrinks. The prediction stabilizes. For 3I/Atlas, the opposite occurred. Each refinement introduced new deviations. Small but persistent, the predicted path kept shifting. Not randomly, not in the chaotic way that measurement error would produce, but systematically, as though the object's actual motion was being influenced by something the models were not accounting for. Solar radiation pressure was considered. Too weak to explain the magnitude. Outgassing was reconsidered despite the spectral evidence. Still insufficient. Gravitational perturbations from nearby planets were calculated. Already included in the models. Nothing worked. The trajectory kept slipping away from predictions, week after week, month after month, always in ways that suggested an additional force, an unseen influence, something pushing or pulling the object in directions it should not have been moving. Some researchers began quietly adjusting their models, adding a hypothetical mass to their calculations, a second body traveling alongside 3I/Atlas that could account for the gravitational anomalies. This adjustment improved the fit significantly, but it also raised an impossible question. If the models worked better with two objects instead of one, was there actually a second object? And this is where the tracking data stops making sense. Anomaly number 3, climbing back toward the outer solar system, and eventually vanishing into the interstellar void from which it came. The entire visit will last only a few years. A brief cosmic moment, a flicker of time in the life of a traveler that has journeyed for eons. This is what should happen. This is the expected trajectory of a simple interstellar object passing through our solar system. A straightforward gravitational encounter. Nothing more. But the tracking data tells a different story. As observatories refined their measurements, the trajectory began to shift. Not dramatically, not in ways that suggested catastrophic error, but persistently, stubbornly, in directions that required explanations the standard model could not easily provide. Each refinement pushed the predicted path slightly away from where pure gravitational calculations said it should be. Each new observation window introduced small deviations that accumulated over time. For a comet, this would be expected. Outgassing jets can push a cometary body in unpredictable directions. But early spectral analysis showed no significant outgassing from 3I/Atlas. The object appeared relatively inert, rocky, quiet. So why was the trajectory shifting? Why did each orbital solution require adjustments that should not have been necessary? And why did internal tracking logs begin referencing something that was never announced to the public? These questions emerged slowly, quietly, in the margins of scientific discussion rather than the headlines. Most astronomers attributed the anomalies to measurement uncertainty, to the difficulty of tracking a faint object at extreme distances, to the normal challenges of interstellar object observation. But a small number of researchers noticed something else. Pattern. A consistency to the inconsistencies that suggested something more than random error. And it was in their leaked notes that the first mention of object B appeared. The first was 1I/Oumuamua, detected in October 2017. A strange elongated shape that tumbled through our system and sparked years of debate about its true nature. The second was 2I/Borisov, spotted in August 2019. A more conventional cometary body that behaved largely as expected. And now the third, 3I/Atlas. The confirmation process was rapid. Multiple observatories verified the trajectory. The hyperbolic excess velocity was calculated. The object was moving too fast to have originated from within our solar system. The math was clear. The conclusion was unavoidable. We had another interstellar visitor. Initial observations suggested a relatively small object. Estimates placed its size somewhere between 1 and 10 kilometers. Its composition appeared rocky or carbonaceous based on early spectral analysis. Nothing immediately unusual. Nothing that would raise alarm bells. And yet, from the very first weeks of observation, small inconsistencies began to appear. Not dramatic, not obvious, but present. The kind of inconsistencies that experienced astronomers notice but rarely discuss publicly until they have explanations. The brightness was not stable in the way it should be. The trajectory refinements required more corrections than typical. And certain observation windows produced data that did not match predictions. At the time, these were treated as minor issues. Measurement uncertainties, calibration problems, the normal noise of observational astronomy. But they were not noise. They were the first cracks. The first hints that 3I/Atlas was not behaving like a simple interstellar rock passing through our cosmic neighborhood. Something about this object was different, and the deeper astronomers looked, the more those differences multiplied. We now know that there are 6 documented anomalies in the tracking data. 6 observations that do not fit the standard model of a single inert object passing through our solar system. But before we examine those anomalies, we must first understand the expected path, the trajectory that 3I/Atlas should be following, and the timeline of events that brought us to this moment. Because only when you see what should be happening can you recognize how strange the reality truly is. Let us trace the journey. 3I/Atlas entered our solar system from a direction in the constellation Lyra. This places its origin somewhere in the general direction of the star Vega, though at interstellar distances, such associations are largely symbolic. The object has been traveling through the void for millions of years, perhaps billions. Its true origin is unknowable. What we can calculate is its path through our neighborhood. The trajectory is steeply inclined relative to the plane of the solar system. Most planets orbit the Sun in a relatively flat disk. 3I/Atlas cuts through that disk at an angle. This is common for interstellar objects. They are not bound by the gravitational choreography that shaped our planetary orbits. By January 2025, when detection occurred, the object was already inside the orbit of Saturn, moving inward, accelerating under the Sun's gravitational influence. The detection was fortunate. Another few months of delay and we might have missed it entirely. The expected timeline unfolds like this. Throughout early 2025, the object continues its inward journey. It crosses the orbit of Jupiter, then Mars, then Earth, each week bringing it closer to perihelion, the point of closest approach to the Sun. Current calculations place perihelion sometime in late 2027. At that moment, 3I/Atlas will be at its nearest to our star. Still tens of millions of kilometers away. Not dangerously close, but close enough for solar radiation and gravitational stress to reach their maximum influence. After perihelion, the object will begin its outward journey, accelerating away from the Sun. And you will learn what specific observations in the coming months will either confirm our suspicions or dissolve them entirely. This is not sensationalism. This is not speculation disguised as fact. Every claim you hear will be grounded in documented observations, and every hypothesis will be clearly labeled as exactly that, a hypothesis. But I will not pretend the data is ordinary, because it is not. Stay with me until the end. Not because I will ask you to, but because once you see how these anomalies connect, you will not want to leave before the final piece falls into place. To understand why the anomalies matter, we must first understand what 3I/Atlas is supposed to be. The story begins with a detection. In the early weeks of January 2025, the Atlas survey system flagged a faint object moving against the background stars. ATLAS stands for Asteroid Terrestrial Impact Last Alert System. It is a network of telescopes designed to scan the sky for near-Earth objects, asteroids, comets, anything that might pose a threat or scientific interest. Most detections are routine. Rocks from the asteroid belt, comets returning from the outer solar system, objects that belong to our Sun, objects that orbit within the gravitational boundaries of our stellar neighborhood. But this detection was different. The object's trajectory was wrong. Not wrong in the sense of measurement error. Wrong in the sense of impossibility. The path it followed was hyperbolic. Not elliptical. Not circular. Hyperbolic. And in orbital mechanics, a hyperbolic trajectory means one thing and one thing only. This object is not bound to our Sun. It entered our solar system from interstellar space. It will pass through, and it will leave, never to return. A one-time visitor from the darkness between stars. This makes 3I/Atlas only the third confirmed interstellar object in recorded history.